Okay, I got another marker. Look at this. Look at this. Look at how many markers I have. They run out. Okay, before I do the Heine-Borel theorem, I would like to take just a moment to prove one of the theorems which we alluded to over here, that that every closed set contains all of its limit points. So, where are we? Here we go. Theorem. S subset, well, actually, it's much more general. It's for any topology. Let me see if this one's better. Okay. S is closed in some topology if and only if S contains all of its lim points. Okay. Well, let's go in the first direction. Let's show that if S is closed, then it contains all of its lim points. All right. Well, we know. So, well, let's just assume off the bat that assume for contradiction. Right, that X is a lim point of S, which is closed, and X not in S. Since S is closed, we have that S complement is open. But then there exists a neighborhood of X which is completely in S complement. But since this neighborhood of X is completely in S complement, we have that this neighborhood of X intersection with S is the empty set. But then X is such that there exists but since this intersection is empty, we can't have it. We can't have that. We can't have that for any epsilon. There exists a neighborhood of X of size epsilon, which contains Y, which is an element of, so let me say it this way, which contains Y, which is an element of S. But then X is not a lim point of S. So in fact, I did use a ball of radius epsilon and so forth, so maybe this S does have to be a subset of Rn. Okay. So now we must now show that if S contains all of its lim points, then it is closed. Okay. Well, to show that it is closed, to show that S is closed, we need only prove that S complement is open. Right? We need to only prove that S complement is open because that's the definition of closedness. That's not even a theorem. Well, let's consider X in S complement. Assume that for any ball or neighborhood, for any n of x, there exists a y in n of x and y not in S complement. So in other words, assume that S complement is not open. And what does it mean for it to not be open? It means that every neighborhood surrounding X contains a Y which is not in S complement. But then, Y is in S, making X a lim point of S and X in S by assumption. And that's a contradiction. So that's the end of the proof. Okay, now, theorem. So this is called the Heine-Borel theorem. S, a subset of Rn, is closed and bounded if and only if well, we could say shorthand, but then I will elaborate. If and only if S is compact. All right, this is a better phrase. Well, what does it mean to be compact? What I mean is that every open cover of S has a finite subcover. Okay. This is the theorem that we want to show. Proof. Has a finite subcover. All right. Assume S is closed and bounded. and assume S is closed and bounded. Well, if it's closed and bounded, then we can consider we can consider an open cover of S. We can call that cover C. And what is C? C is this. Whoops, this is not working out. So it's the set of UIs such that UI is open, and the union over I of UI contains S. Okay? And this, of course, is an infinite cover in principle. Now, for each X in S, define U of X max, U of X max to be, well, let's take it one step back. For each X in S, there exists several UI. We could say UI 1 to N with UI containing X, and N greater than or equal to 1. Okay. Each UI is open, and so there exists a ball centered at X of radius epsilon, which is entirely contained in UI. In fact, we could say there exists a ball, we could call it B, let's say B. There exists a ball, and each UI will have a different, so we call it epsilon max. Let me rewrite. There exists a ball centered at X of radius epsilon, which is entirely contained in UI. For all such balls, consider epsilon max to be such that B X epsilon max contains B X epsilon, which is contained in UI. So there is a for any UI. In other words, there is a ball which is contained for any UI, and B X epsilon max is contained, say, in U max, which contains X. And we call this U max. U max is the one which contains this ball of epsilon max, and epsilon max is greater than or equal to epsilon I, where epsilon I is is greater than epsilon I for any epsilon I such that bx epsilon I is contained in ui. All right, so in other words, each x has a ball of max of epsilon max. Now I claim that the infimum of all such. Now let's consider. We could say, since each x has this property, we could say that epsilon max is associated to a particular x. And so each x has its own epsilon max. We could say epsilon x max is the one that corresponds to this particular x, epsilon super x max. Now, the claim is that the infimum over all x in S of epsilon max x is non-zero. That is the claim. Now, this is a little bit of a nuanced claim, and it follows from the fact that S is closed. Okay. Well, clearly, for any x, epsilon max x is going to be the maximum value between well, let's say it this way. All right, let's say it this way. All right, we claim that the infimum of x in S of epsilon max x is not zero. Suppose it was zero. That the infimum of x in S of epsilon max x did equal zero. This would mean would imply that there is a sequence. You could call this sequence xi, I equal 1 to infinity, which is entirely contained in S, with the property that epsilon max x I is less than epsilon max x I minus 1. And greater than 0. Right? So, in other words, that this is a sequence of terms whose maximum epsilon decreases as the terms go on. That's what it means for the infimum to be 0. This is a closed. So I don't know if you noticed, but the last video ended abruptly, and the reason is because though I finished the recording got corrupted, and so at the end of it got killed. So I will bring us back to where we were at the end of the last one. I think we just made the argument that if the infimum was equal to 0, then there is a monotonically decreasing there's a sequence xi and s which has the property that the max epsilon associated to that xi is going to be, well, it's greater than 0, but less than the previous one, so it's decreasing. That's what the infimum equaling 0 means. Moreover, it's monotonic. Since this is a sequence in S, and S is closed and bounded, the Bolzano-Weierstrass theorem, which we proved earlier, states that there must be a subsequence which converges to a value x in that set itself. But since x is in that set, it must have its own minimum epsilon, which we already discussed, and that epsilon, not minimum, maximum epsilon, I apologize, and that epsilon max satisfies the property that a ball centered at x of radius epsilon max x contains x and is a subset of some open set u sub x in the covering. And now this is a continuation. So now consider this next. As you see, the video did end up going quite extensively after the file was corrupted. Okay. Now, since this subsequence converges to a value in x, which follows from the theorem, because S is closed and bounded, there must be some capital N for which all of the elements in this sequence converging to x are within the ball centered at x and of radius epsilon max x. For any n greater than this capital N, right? Because that's what it means for x to be a limit point. But then, the maximum epsilon associated to each of these xi sub n's must be at least greater than or equal to the maximum epsilon surrounding x minus the difference between x sub I minus the difference between that value x sub I and x itself. And this over here is, of course, greater than 0, since by definition, the difference between x sub I and x is going to be within epsilon max x, because x sub I n is within this ball. In order for, since you don't see me writing it live, it might be a little bit hard to follow. So let me draw a graphic of this. Well, if this is x and this is that ball centered at x of radius epsilon max x, then any y here will be such that there is a ball centered at y, right? And the radius of this ball will be at least, since the open set surrounding x also surrounds the point y, the ball which contains y and which is entirely contained in the open set containing y will have a radius of a minimal radius or a max, at worst case, the maximum radius of this y will be this radius right over here. And what is this radius, r? This radius is the total radius minus the distance between them. That's what we have here, x max minus the distance between them. Okay. Now, this epsilon max xij is going to be monotonically increasing, because as y approaches this value x, the ball increases in its size. Oh, but if it's monotonically increasing, then it's impossible for the infimum to be 0, right? Again, this is a subsequence of a sequence which was said to be monotonically decreasing in its value epsilon, but we just found a subsequence which is monotonically increasing in its value epsilon, and therefore the infimum can't be 0. Okay, so now that the infimum can't be 0, we consider this big ball. There's going to be a big ball which surrounds the entire set S. So the ball is centered at 0, and its radius is the maximum norm of any x for x in S. So of course this ball contains S. This ball is as well open, and so is S complement, since S is closed. Well, if S complement is open and so is this ball, then the ball intersection with S complement is also open. Again, the reason for that is because, well, if the ball is open, then there exists a neighborhood n1 within the ball which contains x, and an n2 in S complement which contains x, since S complement as well is open. But that means that if you take the minimum value between n1 and n2, in other words, either n1 contains n2 or n2 contains n1, since both of them contain x, and since both of them are balls, therefore you take the minimum such ball, and that minimum, either n1 or n2, whichever one is the minimum, is a subset of B intersection S complement, and so for any x in B intersection S complement, there's a neighborhood which contains x, and which is entirely a subset of B intersection S complement. Now we can consider x on the boundary of S. Of course, x, the boundary of S is in fact contained in S because S is closed. So we select one such element, and we select from our open cover C a subcover C prime, which will be finite. And we will demonstrate now, since S is closed and bounded, we will show that we could get this finite covering. We do it by iteration. The first C prime, we take the open cover in C, which contains X, and which has a ball in it of radius epsilon max S, contained in this open cover. Again, where U max X contains a ball centered at X and of radius epsilon max X. Of course, epsilon max X is non-zero. Consider some other X on the boundary of S, but which is not already in our subcover. So this is an X on the boundary, but X cannot have been covered by this first open cover. And what we will do is we will now say that the open cover is what it was, union with this new open set from the original cover, which contains X prime and which has a ball surrounding X prime of radius epsilon max X prime, just like before. We do this until the entire boundary of S is covered, and of course that is certainly possible since the boundary of S is covered in the original open covering. Now the question is this subcovering for the boundary, is the cardinality of it infinity or not? We claim that it's not. We claim that the cardinality is going to be less than infinity. The proof is because if we assume that the boundary was infinity, it would mean that for all the x's in the boundary which generated this open subcover, there are infinitely many of those such x's, right? Because to say that the subcover is infinite is to say that we took infinitely many open covers, and therefore, since each open cover was associated to a point in the boundary which was not included in the subcover which was generated until then, it follows that we have infinitely many such points on the boundary. But that means that the length of the boundary is going to be equal to the length of all of these epsilon maxes. Again, because each time you add a new cover, you're covering at least an epsilon max more of the boundary. Okay, but then that means that the length is going to be the sum of the two of all of these epsilon maxes, but that's greater than or equal to the sum of the infimum over all the x's on the boundary of epsilon max x. You see, this is a constant, and it's the minimum of these, and we're taking infinitely many of them. Now, if this was 0, this would be this over here would be 0, and we wouldn't know anything about this because it's only greater than or equal to 0. But since we've already established that the infimum is non-zero, right? But since the infimum of x in S, not only in the boundary but in S itself, the infimum of epsilon max x is greater than 0, we have that the length would be infinity, but that would contradict the boundary, the boundedness of S. Now, I mentioned when I wrote this, here, the length of delta S equals infinity, this contradicts the boundedness. I mentioned when I wrote this that, the boundary might be infinite even if S is bounded because of some fractal, but But it doesn't matter because what you could do is you could consider the trace around the boundary of lines. Instead of the boundary, consider just lines between each of these generating x's, and you would find that the lines between each of the generating x's, the sum of that will be infinite. And that's not possible for a bounded set. Okay, because it's lines, it's not a fractal. We then continued on to here, and we argued that this could be repeated now for the new boundary of S. In other words, S, the boundary of S was covered. Indeed, the reduction of the covering is going to be at least the minimum epsilon max x for all the x's on the boundary. Some of the balls might be bigger than others, but you take the smallest one is going to be greater than 0, and so the S's size has now been reduced by at least the smallest epsilon. But in any event, we claim that we could again do the same process for the new boundary. In other words, S, take away that part of S which was already covered. Okay. Now the question is, well, will this be infinite? We claim that the answer is no, it will not be infinite. In fact, it will be finite. This will again be finite, for otherwise the maximum difference between any two elements in the set, the supremum over all the elements in the set, will be equal to, and this needs to be a little bit corrected, I equal 1 to infinity of some subsequence xji, where xji lie directly on the lines connecting xi and xj. Now, in case it was infinity, this would have to be an infinite sequence of a subsequence, but since each term as well is non-zero, this is going to be infinity, which contradicts our assumption that, again, S is bounded. Okay, then we went to prove the converse statement, right? We just showed that if S is bounded, then we could find an open subcovering. Now we want to show that if every open cover of S has a finite subcovering, then S is closed and bounded. So the proof is, well, it's clearly bounded since the subcover is made up of a finite number of open covers, and each open cover, of course, is bounded, and so the finite union of open covers is bounded, and of course, that is, you could assume by contradiction, though I didn't do it over here, you could say, oh, well, maybe it's not bounded. Well, if it's not bounded, that means that there's an element in the union which has or a sequence in the union whose supremum norm is infinity. But that means that there is a sequence, at least in one of them, whose supremum norm is infinity. But that means that one of them is not bounded, but that's not possible for an open set in S. Okay. Since each UI is bounded, clearly the finite union of bounded sets is bounded. So lastly, we needed to show that it was closed. To show that it's closed, to show that S is closed, we need again only demonstrate that S contains its limit points, right? As we showed before, there's a theorem, and we demonstrated and proved it. And I think that's in the other video. And I will try to connect this video to that video. We showed that a set is closed if and only if it contains its limit points. So we need to now show that if X is the limit point of S, then it is contained in S. So assume for contradiction that X is a limit point of S, but X is not in S. Then we may construct an open cover of S which has no finite subcover. Why? This will be the open subcover. Namely, for each Y in S, let the ball centered at Y of radius R sub Y be a ball surrounding Y with R sub Y equal to the distance between Y and X divided by 2. Now, clearly, since X is not in S, R sub Y will be greater than 0. Again, the reason is because this is for all Y in S. But if we're taking all Y in S, Y, and X is not in S, then Y can never equal X, and therefore this will always be greater than 0, and so it divided by 2 will be greater than 0 as well, for all Y in S. Further, of course, the grand union of all of these balls is an open covering of S, simply because we did it for all the values Y in S, and therefore, automatically we covered everything. If there's a y which we didn't cover that y with a ball centered at y of radius y minus x over 2. Okay. Now, so let is an open covering of S. Now, let y in S. No. Let C. This is going on the upper part. Let C prime be a subcover of C, which is finite, and C prime is the union of these balls, right? We assume, for contradiction, that every open cover has a subcover, and yet S is not closed. All right. Well, that means that we can find the subcover of this particular open cover, but then since it's finite, there must be some R min. In fact, you could just simply go through all the instances I equals 1, I equals 2, I equals 3, and just find the R sub yi, which gives you the minimum radius. In other words, find the y which is closest to x in this subcover. But what does that mean? Well, if we do find such an R min, again, R min is the minimum over all I of Ri sub I, Ry sub I, where I goes from 1 to n, then we can consider a y prime in S with y prime minus x less than R min. And I said a note over here, y prime exists since x was said to be a limit point of S, which means that no matter how small of a neighborhood you consider around the point x, there will always be a y in S, which is in that neighborhood. In other words, there will always be a y prime in S whose distance is going to be less than any R min, so certainly less than this R min. But that means that y prime is not in the grand union, because if it's less than R min, then the difference between y prime and the y min associated to this R min is going to be greater than R min, and so it won't be covered in that ball. So that means that this is not a finite subcovering, which means that we can't have a finite subcovering if x is a limit point and is not in S, which means that x cannot be a limit point simultaneously as not being an element in S, which means that if you could have a finite subcovering, that means that S contains all of its limit points, and that was the end of the proof.